Okay, 3.5, continuity and end behavior. Basically, we're going to be looking at graphs and determining where the graph is discontinuous. And also, we're going to look at the end behavior of graphs. What's happening way out at the ends? The graph going up, down, is it approaching some number? So let's first define what exactly is a continuous graph. And I think the easiest way to discuss that is a continuous graph is a graph that you can trace without lifting your pencil. If you have a picture of a graph and you can click your pencil and put on it and trace the entire graph that you see, it's continuous. So discontinuous, a graph that you cannot trace without lifting your pencil. So you're tracing a graph and you have to lift your pencil to move to a different part of the graph, then it's not going to be continuous. It is now discontinuous. There are different types of discontinuity. Three, to be exact. Number one, infinite discontinuity. This occurs when a graph breaks to the infinity at a given x value. And we'll see a picture here in a second, but literally, you will see the graph break. It's like someone grabbed it and just broke it and bent part of the graph up and part of the graph down. Okay, so the graph is going way up to infinity at a certain x value and way down to negative infinity. Or they both broke upwards. They could both approach positive infinity or both approach negative infinity. This is caused by a domain restriction, specifically a fraction. So if you have a domain restriction caused by a fraction, that means, do you have anything that would cause a zero in the bottom? Because you can't have zero on the bottom of a fraction. If you do, you are going to have probably an infinite discontinuity. Now, if you have the same situation where you have a domain restriction caused by a fraction and it cancels out, that would cause the next type, a point discontinuity. So we have infinite, now we have point. A point discontinuity literally means a point is missing. There's a hole in the graph. This is caused again by a domain restriction, fraction, but the restriction cancels out. And we're going to see that in an example. Okay, so the original function had a restriction. We maybe factored something, and we found out that it can be canceled. If it cancels, then instead of breaking to the infinities, it's now going to have a single point pulled out of the graph. There literally will be a hole in the graph. And the third discontinuity is what's called a jump discontinuity. Now, jump discontinuities usually occur in special functions. Okay? Basically, there's a break in it. Not a single point, but you're going to have to jump over several points. A piecewise function would cause that. A step function, or it's also called the greatest integer function. Okay? Those would all have breaks in it. Okay, we're going to look at three graphs here to explain those again. So we have infinite, point, and jump discontinuity. Okay, so here we have a graph. Here's an example of, it says right here, infinite discontinuity. So we have this function, -1 over x minus 2. If you wish to put it into your calculator, you can. Okay, but basically this is what the graph's going to look like. As you can see, at x equals 2, we have a break. One part of the graph is breaking up towards the infinity, positive infinity. The other part of the graph is breaking down towards negative infinity. So this part of the graph is going up forever to positive infinity. This part of the graph is going down forever to negative infinity. Okay, so it's breaking to the infinities. Where is that occurring? Well, wherever we get a 0 in the bottom. What number would cause a 0 on the bottom? That number is 2. 2 minus 2 would give us a 0. It's not going to cancel out. So that's what's causing an infinite discontinuity at x equals 2. And you must specify where it is occurring. Okay, let's take a look at this next one. Now the original function is x squared plus x minus 2 all over x minus 1. Okay? The top can be factored. Okay? But before we even look at the factor, what's not going to work down here on the bottom? 1. 1's not going to work. 1 minus 1 gives us a 0. So that's where we're going to have the issue. Okay? At x equals 1. We factor the top and we see that x minus 1 is actually going to cancel out, leaving us with x plus 2. So we said there was a restriction at 1 in the original. Even though it cancels out, it was part of the original function. So we will now have what's called a point discontinuity, or a hole in the graph. I'm actually going to graph this one, because we can actually zoom in and see the hole in the graph. So we have x squared plus x minus 2 divided by x minus 1. We'll start with a zoom 6. Now we're getting a straight line, okay, because of this. The result, when something is canceled out, we're actually going to see the graph of y equals x plus 2, which we do see. Okay, we can clearly see that that is touching the y-intercept at 2, slope of 1, up 1 over 1, up 1 over 1, and so forth. But based off of the original, there should have been a discontinuity at 1. Well, it looks fine to me. We do a second trace and calculate the value at x equals 1, you're going to see it's not so good. It's not so fine. We can clearly see right here that y equals nothing. There is absolutely nothing there. That tells us there's an issue. Because if we calculate the value at something else, say at 2, well, there's 4. It's a point. 2, 4 is a point. If we go back to 1, we have 1, nothing. There's no point there. Okay, so I'm going to change the window so you can see that. I believe I go 0 to 2 on the x min and max. We should be able to see that hole. And there it is. Okay, there is one single point missing. Can't see it on the original, okay, because the calculator just didn't show it because of the pixels. But if you zoom in, okay, or change the window so you can see it, there's actually a hole in the graph at x equals 1. Now, if you want to know where that hole occurs, you plug 1 back into the x plus 2. So 1 plus 2 is 3. So this hole is occurring at 1, 3. That's where the hole is. That's a point discontinuity. So if the restriction cancels out, it's a point, not an infinite. And the last one is an example of a special case. Here we have the greatest integer function. Some people call it the step function because it looks like steps. We can't trace this. We go over here. I have to jump. I literally have to pick up my pen and jump every time I get to the next step. I'm not just moving over a single point, so it's not a point discontinuity. I actually have to jump over several points to get to the next one. So there's a jump discontinuity at every integer. Okay, so x equals 1, x equals 2, x equals 3, x equals negative 1, x equals negative 2, x equals negative 3. All of those would be jump discontinuities. again, if you're watching a recording, you can pause this at any time if I'm going too fast. All right, let's take a look at an example. We're going to determine whether each function is continuous or not. If not, name the type of discontinuity and where it occurs. Very simply, if you have a function and there is no fractions, unless it is a special function, it will be continuous. Okay? Here we have a regular function, f(x) equals 3x squared plus 7 for part A. It's a quadratic. There's no restrictions. We automatically write that it is continuous. That's it. There's no way that we can have the bottom to be equal to 0. There's no infinite, there's no point, and it's not a special function. We have to worry about jumping. So that's it, you're done. You want to look at the picture? We can. (3x squared plus 7). Now, we just took a test on transformations. We know what the basic graph of x squared looks like. It's a parabola, minimum at the origin. The 3 is going to cause a vertical stretch or vertical expansion by 3. 7 is going to move it up 7. So it should be moved up 7 from the origin and stretched vertically. Now, let's change the window so we can see more of it. Let's make the x max 50. Oops, sorry, I changed the wrong one. I meant the y max. So let's make the y max 50. There we go. So there it is. It's been moved up. There's no discontinuity. Everything's perfectly fine. Part B, there's some work. All right, the bottom is a problem. The bottom is a difference of squares. We need to factor the bottom to determine where we have an issue. The issue is no zeros on the bottom. So what values of x will give us zeros on the bottom? In the first case, a -2. In the second case, a +2. So that is where our discontinuity should be. The question now is, what type? Well, does anything cancel out? Okay. Does anything cancel out? The answer is yes. X minus 2 cancels with x minus 2, giving us 1 over x plus 2. So, x equal to 2, okay, x equal to 2 is going to be a point discontinuity because that restriction canceled. X equal to -2 is still part of it, okay? That's what's causing this right here. X equals -2. It's still there. I can't cancel it. So that's going to be infinite. So based off of just looking at the algebra here, I'm going to say that we have an infinite discontinuity at x equals -2. And we're going to say we have a point discontinuity at x equals 2. Let's prove it. Let's take a look at the picture. I'm going to type in the original. Okay? X minus 2 divided by x squared minus 4. Now the result should look like 1 over x plus 2. It's a rational function. Okay? Should look like a hyperbola. And there it is. Now, this calculator does not have the ability to get rid of that vertical line here. Okay, there's a vertical line right here. Okay, if you can follow my cursor. Okay, that should not be there. Okay. The older calculators, this is an 83, okay, shows that. It connects up the two lines. What the graph really looks like, draw it down here. Okay, what this really looks like is at -2. Okay, the graph's going to break. And at 2, okay, if we plug 2 back in, 1/4, so 2 1/4 have a hole. Okay, so here we have, graph comes down, and keeps going. So that's what we're really seeing there. So we have an infinite discontinuity. That vertical line kind of helps us decide where that's occurring. Okay, you can clearly see here at -2, that's where it's breaking to the infinity. 2, we can't really tell what's happening. Again, we can calculate the value at 2, and there's nothing there. So there's definitely a hole. We plugged in 3, we get 0.2, which makes sense because 1/3 plus 2, 1/5 is 0.2. Okay, if we plugged in 0, we get 1/2. X equals 0, we get 0.5. But at 2, there should be nothing because of that restriction. It canceled out, the x minus 2. So infinite and point for that one. Okay, part C. All right, part C. Already looking special, piecewise. Okay, so pretty good chance of a jump discontinuity just based off what it doesn't have to be a jump, but there's a good chance it could be a jump. This could be continuous. They might connect up. It might be a hole right at one point where they connect up, or there might be a break, which would be a jump. Okay, we have to graph it to find out. So in order to graph piecewise functions, we need to make tables. So we have our x and we have our y. Now, 1/x is restricted. It says if x is greater than 1. So 1, 2, 3, those values work. If I plug in 1, I get 1/1, which is 1. I get 1/2, which is 1/2, 1/3, which is 1/3, and so forth. I'm going to circle 1, 1. The reason why I'm going to circle 1, 1 is because an open dot is occurring at 1. It says x greater than 1, not 1. I am going to include 1 because that is my endpoint. And there will be an open dot there to say that we don't include it. But 1.0 forever 1 is going to work. So something very, very close will work. 1 actually doesn't. Now for the second part, okay, we have x is less than or equal to 1. So that's definitely going to be okay. So we go 1, 0, -1, and so forth. 2, 1, 0, and so forth. I'm not going to circle anything because they're all solid dots. So let's take a look at this graph. 1, 1, open dot. 2, 1/2, solid. 3, 1/3. So what's going to happen is it's going to keep getting closer and closer and closer to that axis. It will never, ever, ever go below it, though. Think about it. If I plug in a larger and larger and larger number, I keep going bigger, say like 1,000,000. 1 divided by 1,000,000 is a positive number, but it is tiny. 1/1,000,000 is like 0.0 whatever. It's very, very, very small decimal. It will get closer and closer and closer and closer to the x-axis, but never touch or go below. Second part, okay, 1, 2, solid dot. 0, 1, -1, 0, and so forth. That continues on forever. Okay? So where's our discontinuity? Do we see a break anywhere? Of course. We see a break at x equals 1. What time? Well, in order to get from one point to the next, I have to jump. So we do have a jump discontinuity at x equals 1. All right. Next section, end behavior. Okay, new topic. All right, talked about continuity. We're also going to talk about end behavior. And there's one more topic we're going to talk about, is increasing, decreasing. Okay. End behavior is probably the last thing we're going to talk about today. We'll talk about increasing, decreasing tomorrow. End behavior basically asks this question. What's happening to the graph? Can you go way left or way right? And this is the notation that we use. The limit f of x as x approaches negative infinity. Lim, L-I-M. Oh, that's right. What's happening? Limit basically saying what's happening. F of x represents y. So what's happening to y when x goes to negative infinity? When x goes way left? What's happening to y when x goes way left? That's what this is saying right here. Oops. What's happening to y when x goes way left? And this is saying what's happening to y when x goes way right. It's notation you have to learn. Limit of f of x as x approaches positive infinity. Limit of f of x as x approaches negative infinity. What's happening to y when x goes way left? What's happening to y when x goes way right? All right, let's take a look at an example. I think that's the best way to approach this. All right, describe the end behavior of this. Negative 2x cubed. Maybe you know what this looks like, maybe you don't. Y equals x cubed is a basic rate. Basic cube. The negative is going to cause reflection, the cube is going to stretch it. So y equals negative 2x cubed is going to basically look like this. If you're not sure, you can always confirm it with your calculator. Negative 2x cubed. So the question is, what's happening to y? What's happening to y? What's happening to y? So, start the origin. To the left. Is the graph going up or down? So start the origin. To the left, the graph is going up. It goes up forever. We call that that's your answer. It goes up. Starting at the origin. To the right. I'm approaching positive. Where's the graph going? Way down. The negative is here. Negative. So, what's happening to y as x goes way left? So approach negative infinity, it's going up. What's happening to y as x approaches positive infinity? It goes to the right, it's going to way down. Actually, we ran out of time a little quicker than I thought, so I'll finish up the rest of these examples tomorrow, and we'll also talk about this.